So hello everyone, this is the advanced section of a mini course on computation. And today we're going to have Simon talk about something very related to the first lecture of the physics module. Yeah, so how about Simon, you can first introduce yourself a little bit and then the stage is yours.
Yeah, sure. So hi everyone, I'm Simone, and this will be a lecture that I hope you will like. And I'm pretty open to questions we can discuss at the end. So let's get started. There's an introduction. I'll give an overview. So since we started lectures with a quote, I thought about sharing this quote, which is kind of ironic. So I hope you will understand something from this lecture. It's not really like rocket science, but I may be not very good at explaining. So please ask questions if you don't understand something, and feel free to do it. So about me, I'm a master's student in data science in Italy at Bocconi University. I don't really have a deep interest in something. I'm still studying, so I'm kind of exploring subjects at the moment. I like coding, and some acknowledgements thanks to Chi-Ning for allowing me to do this. And most of the contents of this lecture are from a course I had in my bachelor studies. So thanks to these two professors, I was able to have this kind of experience. So let's get started. This is some notation I will use, just colors, definitions, theorems, proofs, and examples. So what is simulated annealing? Simulated annealing is a method that allows us to solve complex problems which are nonlinear and have a very difficult way of solving them, let's say. We will see what this means precisely. The first application that was given the name of simulated annealing was to the traveling salesman problem, which is a very famous problem that we will also introduce. It is a meta-heuristic problem that uses statistical mechanics concepts. So this means that it's not an exact solution, and we will derive its properties, but it doesn't allow us to find the perfect solution to a problem. It is a perfect example of inspiration from nature and from things that we can observe in reality. It's not, okay. Okay, it just got stuck. What we will do, we will recap some contents from the lecture we had, lecture 2a. We will also present a problem, and oh, sorry guys, I don't know how it's getting stuck. Okay. Okay.
Are you using like a presenter mode or?
I'm using presenter mode, I think. I don't really know. I found it out. There's a button here, so I can do it.
Oh, okay.
We will propose a setting that helps us ease this difficult problem and derive an algorithm that achieves this solution, this not precise solution, but satisfactory solution. What we saw in statistical mechanics is that we have microstates and macrostates. Microstates are many and not observable, and they denote a probability distribution over the sample space, which is big omega here. Macrostates are properties of these microstates that are common to many of them, and they are usually a mapping of these sample space to R. So they're a number like temperature or something else. The problem is that over time, we see only one butterfly effect. We see only one outcome of the many possible parallel universes in the film cinematographic example. And so we cannot really see the space of the sample. We cannot see the sample space. We see only one outcome of reality. And with thus, we have to make additional assumptions to derive properties of the whole distribution from a single observation across time. This is, okay. This is not funny. My computer is lagging. Okay, so an example in thermodynamics we saw in class is thinking of microstates as the configurations that particles can have. And these particles are very small. There are so many, we cannot measure their single energy. But in the macrostate, we can just measure the temperature and get a feeling of how these configurations can be. Still, we cannot observe the specific setting of the microstate because there's many ways of obtaining a single temperature from configurations. In the simple example, we can think that if we have k distinct particles and we wish to order them in a grid, the solution will be combinatorially exploding. So this is not an easy way to see the solution to the problem of understanding which configuration we're looking at precisely. And this is also an easy example. There's a lot of relaxations. So if you want to see something else, click on the link and you'll see a question I asked. What we have in hand is what we don't have in hand is the ensemble average, which is the first moment, the average of the real distribution, which we cannot see. What we can see is the time average, which is the average of a single realization over time and not of all the realizations we could have seen. With additional assumptions, we can say that they are the same, but we need to make these assumptions. And if this were possible, we could sample iteratively and just get to the mean by doing the mean of the over time observations. What Boltzmann thought is that he could map the distribution, giving it a characterization that was through energy. And we will see why this is important for us. But basically, he assigned a feature to a distribution to give it a shape in the probability space. Z is the element that normalizes the energy configuration, meaning that if we have a feature given to a single realization, we can use Z to set this probability to a number between 0 and 1 because it is the sum of all the possible outcomes, all the possible energy outcomes. But the Z is big because it's a sum over all microstates. So we cannot really use it, and we have to find a way to avoid using the whole Z. And Z also depends on temperature because it's the denominator of the distribution that Boltzmann derived. It is, though, a link between configurations and energy, which helps characterizing a microstate with its macrostate. And this also gives us a link from the reality we can observe and the reality we cannot observe, and is thus helpful somehow. The application we will see is the traveling salesman problem, which is a very famous problem. It is not yet easy to solve, let's say, but it's rather easy to explain. We just have n cities and the matrix with all the possible distances between each city. And we wish to find a tour which visits all of them without passing twice on the same one, which starts from a city and ends in another city. Looks like it's simple, but we will see that this is really not the case. In a formalized framework, we could say that we wish to find the minimum energy distance, the minimum energy where energy is distance, configuration of the routes. So the minimum distance route, which is this one, over the space of possible routes, which is this R. Let's see how complex this is. Let's say we wish to find the minimum one by enumerating all possible configurations. So for each configuration, we just see what's the distance and find the lowest one. If we have 30 cities, this will mean that we need to find all the possible orders of cities. If we have 31, let's say, just to make 30 factorial, these possible orders are 2.65 to 1032, assuming we can make more than 1 billion operations per second, where these operations are looking at the distance, so calculating the distance for a single route. We will need a total time of 2 million stories of the universe, assuming the universe is this billion years old. I don't really know about it. It's the first result on Google. But the thing is that if we have just 30 cities, which is basically like a normal province anywhere, if we wish to find a minimum distance, in the worst case, this is going to take us some time that we cannot really take to find a solution. So we cannot really do this. Indeed, TSP is NP hard, which means that it is at least as hard as NP complete problems, and it is very, very difficult to solve. The proof is that TSP is combinatorially exploding, and it is thus not tractable in terms of the worst case scenario and enumeration. The real proof is a reduction of the Hamiltonian cycle problem that is part of the NP complete problems. So TSP is very difficult to solve. We could find like greedy solutions like this one, which is a little more like structured than the first one. We just wish to find a tour of the cities satisfying some constraints, which are no subcycles, because it's a tour, so no subcycles, and that the degree of the cities is less than 2, because each city is just connected to 2 cities. And if we do this, the computational time is pretty slow, but we will not find the exact solution, because you can think of this as seeing that it's not really true that finding the lowest distance solution starting from single city and then iteratively adding this is not going to be necessarily the lowest distance solution overall. Nevertheless, we can also see that using the concept of approximation algorithm and big theta bound, which is just like a function bounding another function, we can see that this algorithmic solution is theta log n longer than the exact solution of the algorithm, of the TSP problem on average. This means that indeed it is not really super long, and it is also shown to be 15-20% longer than the solution given by the Heldkarp algorithm, which runs in exponential time. So this greedy solution of just like doing the most intuitive thing is not really bad. It is not bad. However, this does not mean that we are solving the problem, because we're not finding the minimum distance configuration, and we are not giving a framework to find the exact solution every time. This does not generalize to all TSP instances, and does not guarantee to find the minimum distance configuration. So it's a heuristic method that gives good results, but still, it's not really enough. So we can think of something more, let's say, well thought. We can think of finding a way to sample configurations in an efficient way, because we need to do it in efficient time, that does not necessarily get stuck at local minimas, and that exploits somehow this distance distribution to sample in an intelligent way, and explores the space in a deeper way than a greedy algorithm. This is just a notation observation. The R will be addressed also with I or J, so just keep this in mind. We have that the route space is the space of valid routes, so tours that go from a city and get to the starting city, exploring all possible cities. And we have a feature that we can assign to the cities that in our case will be the macro state measurement, the distance, the energy, the way we called it before. Given that this macro state, the energy, the distance, is common to many routes at the same time, or to some routes, we could assign some kind of probability distribution to the routes given the feature. If we think of a system that samples distributions, that samples a distribution of routes given another one, we also need to define this transition matrix, which just says that from a point to another, we will have a probability of getting to a configuration given another one at the previous step. In a Boltzmann fashion, we can just say that given a feature, we can express the probability distribution of the routes with this formula, which resembles Boltzmann's formula, where UI is E minus E to the minus the distance over T, where T is a constant temperature. This helps us because it will allow us to treat the decision problem in a precise way that we will see. Still, though, Z is not easy to evaluate. It's actually impossible to evaluate because it's a sum that goes over all possible configurations, so it's combinatorially exploding. We need to explore this further. We need a stationary distribution because we wish to get to the mean of this. We wish to get to the minimum, and we will have that the technical requirement is that the states belonging to the probability distribution are null and recurrent. If you wish to expand it more, I have prepared for you lecture notes that you will see. But basically, this means that given a distribution, if we have a transition matrix, this transition matrix does not influence the distribution itself. So this is invariant to the transition matrix. Still, it is not enough, because if we think about a sampling scheme in which we start from a distribution and we get stuck at this forever, this is not going to be necessarily the best one. And so we do not really wish just this. We wish this process to explore all possible states. We also have to find a property of the process itself. This property is ensured by ergodicity, which we saw in class, which means that basically the time average is almost surely tends to the ensemble average. But basically, it also means that starting from a point, we will eventually, as time goes by, become independent from that point in terms of the distribution. And so if we keep on transitioning the distributions we get with the transition matrix, which depends on time in this case, we will get to a distribution which is independent on the starting point and has explored the space. This distribution will also be stationary. So this will give us more material to work on. In terms of implications, of intuitive implications, stationarity also implies that there's an equilibrium condition. So the inflow and the outflow for each node is balanced. However, also the sum is not really easy to evaluate because that's a sum for all nodes, all states but one, so it's still big. We will assume that there's a stronger relation, which is node with node. That's the detailed balance condition, which implies the global balance condition of the inflow equal outflow for each state, but it's dependent on single tuples of states. So we will assume that the inflow and the outflow of each possible state will be balanced, and thus everything that is given by a state will be given back by the state it is given to at each iteration. This is a very strong equilibrium condition, but it is basically the only one we can easily use, let's say. If we create a process that is able to explore the space efficiently and in a sufficient manner, where it is easy to propose different configurations, which are in line with the configuration we have at the moment. And this proposal is done comparing the distance so that we like make a decision based on the distance we see and the distance we have. We could also, assuming that we always accept proposals that lower the distance, we could basically find an iterative method that explores the space in a more efficient manner. Keep in mind that this does not mean that we will not accept configurations that give a higher distance than the current one. So this is something to keep in mind. We're just requiring to always accept when distance is lowered. Then we will find a way to explore the space in such that we do not get stuck at local minimas. To ease this process, we will assume that there's a proposal and acceptance split. In the end, the transition matrix Q for each position of the matrix denotes the probability of shifting from a state to another. We could split this probability in a probability of sampling a state from another, which is P, and the probability of accepting this proposal, given the one we are seeing at the moment, which is I. These two matrices are matrices of probabilities, and this multiplication is done element by element, Ji, Ji. So this is not a matrix multiplication, so just to keep it in mind. Thus, we need to make some additional assumptions because the problem is still difficult to solve. This can be relaxed quickly, but we will propose the easy example just to make it understandable. If we assume that proposals are symmetric, and we just use this notation to denote the change in energy, where it's actually a change in a feature, and the minus change in energy, because if you remember, Boltzmann distribution has a minus in the exponent. But we can just think of it in terms of changing this feature we have not yet defined. We can, upon additional procedures, I'm not showing because it is indeed intended to be a short lecture, but you can see all the details in the lecture notes I will share. We can assign an auxiliary function to the acceptance matrix, the A matrix, which is designed in a way such that it has specific properties that are just making calculations easy. This auxiliary function is usually derived with specific properties. The most famous one is the metropolis rule, which is this one. So the absolute value of the change in energy. And given this setting and these assumptions, we can just say that the acceptance matrix is going to be the minimum between 1 and the division of the two probabilities of the proposed state and the current state. This looks still difficult because how can we evaluate the probability of a given state if we have to sum over all possible states in the Z, which is the normalization factor? Well, this is not required since this metropolis rule inside the design of the A matrix, which is this one, more details in the lecture notes, basically allows us to reduce the choice to a probability of 1 if the change is positive, which means that the change in distance is negative. Remember that there's a minus. And the exponent of this change if the change is positive. So we can still accept if the change is positive, but if the change in distance is positive, but with this probability, which decays quickly because it's an exponent. So it's not always sure, but we can do this. We can explore configurations that are actually worse. This indeed is equal to the minimum of 1 and e to the delta change of energy, distance, whatever, which is equal to this, to the fraction of distributions of probabilities for the proposed state and the current state. This is due to the fact that if we expand this formula of the exponent, we get that this is the change in the feature, which is minus the change in energy, which using basic exponent properties is just the fraction of the proposed distribution and the current distribution. So if you can see, we found a way to propose states given the distance, avoiding the use of the z factor, which is what makes the problem difficult, because we have a lot of microstates and we cannot really sum over all of them because there are too many. This is an inefficient sum. Yet we can find a way to compare the two distributions with a fraction and create an acceptance matrix, which is dependent on the distance change and assigns a probability to each proposal depending on the previous one, and has good properties, meaning that if the move is beneficial, we always accept it. And if the move is not beneficial, we might accept it with some probability. This probability, however, always depends on the temperature, which is some if you've done machine learning, this is kind of like a hyperparameter. So it is something which influences the decision choice when the distance is increased. And we might need to explore this further. We will give a rule to find a way to use this t in a clever process. Indeed, we see that if t tends to infinity, the distribution tends to a uniform distribution over all possible routes. So if we use t equal to infinity, we will just randomly walk, because we will always accept the distribution of the probability is uniform over all possible configurations. So we will just randomly walk. If t tends to 0, instead, the distribution concentrates on the minimum distance configuration. So we will become highly selective and always accept and only accept distributions that decrease the distance. This is a graphical explanation of the situation we are in. For t tending to, okay, so sorry, I have swapped these. Okay, so for t tending to infinity, the distribution is uniform. For t tending to 0, the distribution concentrates on the minimum distance configuration. This is the energy. This is the distribution assigned given this energy feature to the routes. These two are not really useful for us. So we will need to explore this given a proposal matrix and some additional rules. A proposal matrix is rather easy to think of. It just needs to propose routes that start and end at the same city, have a size of n, and don't have sub routes or disjoint tours. They're just valid routes. So we could think of doing a swap of indices of the cities, and we will know that the routes will be valid, and it will be easy to evaluate the change in energy for this acceptance matrix. This is indeed because if we have two cities which are linked and two other cities which are linked, and we just sample a candidate as a swap of the links, this will be rather easy to do, easy to check, and it will also be easy to see the distance between them. Indeed, the change of energy or of distance is just the distance of the candidate minus the distance of the current route, which ends up being the distance between the exchanged indices, as you can kind of see and not see in this image. So if these two were linked and these two were linked, we just propose a swap of cities, which links cities that were not linked before and keeps the route valid. Indeed, all the other parts of the route are the same. So these parts of the distance evaluation can be kept constant. And if we subtract, one configuration and another in terms of distance, the difference will be just the changing edges of this route. Thus, we have found a way to sample from the space of the routes efficiently and intelligently, yet we saw that we can create an acceptance rule that is somehow intelligent and clever, but this is not enough because the temperature is still a problem, meaning that we cannot really find a perfect temperature. The solution to this is simulated annealing, which is the technique we will introduce now. We saw that 1t is not enough. T is equal to infinity. The distribution is uniform, so we always accept proposals. And we just explore the space like in the first algorithm, where we were just enumerating all possible solutions. Thus, we are just like doing O n factorial operations, n minus 1 factorial, but the O just makes it constant. So we are using a combinatorially exploding number of operations if we want to find the minimum distance configuration in this case. In the case in which t is equal to 0, the distribution peaks at the minimum route, at the minimum distance route, but yet the decision rule becomes very strict. So we only accept proposals that lower the distance, and we get stuck at local minimus if the function is non-convex, meaning that it has ups and downs and is not like a perfect cup. In the traveling salesman problem, it is highly likely that this is the case because the traveling salesman problem is combinatorially exploding. It has lots of complications, lots of complexities in terms of the shape of the distances. It's a difficult instance. Indeed, also for every t belonging to this set of from 0 to infinity, the distribution will like slightly concentrate around the global minima, but the decision rule that comes out from this specific t will not be able to escape all possible local minimas in the worst case scenario. Because think of t as the factor that induces the decision rule. And thus for each t, we can find a way to create an instance of the problem that has an energy function with a very deep local minima, which is not the global minima, that makes this decision rule dependent on the energy switch, not enough to escape the local minima. So it gets stuck anyway. An idea is using all of them. Simulated annealing is indeed a technique used in the creation of materials that have specific properties in it's a physical process that gives specific properties to materials through a process of sequential heating, keeping this material at specific temperatures for specific like amounts of time, such that the material rests at a temperature and like achieves some specific properties at that temperature, and then the temperature is lower, is increased, and this is done sequentially. I'm not really an expert of the physical process of annealing, but the idea is using a single temperature, but using a sequence of temperatures. Now, if we could define a temperature schedule function that starts from infinity and gets to 0 in a decreasing way, such that at each time, at each like time unit, it's either the same as before or a little less, we could exploit this to create a process which starts from a random configuration, R0, and assigns the temperature for each iteration to the distribution we sample from in the distribution to the acceptance rule we use in that specific iteration. Intuitively, this, oh, sorry, you cannot see this last point. Well, yeah, this implies that starting from, which is uniform, and it's just an exploration of the space, we iteratively get more and more selective. Thus, we start from accepting everything, and we gradually accept less and less with this like constant, it's not constant, with this decrease of temperature that allows us to escape all the local minimas that are escapable for a given temperature in the moment in which it is employed. It's not really like super intuitive, but if we think of a non-convex function, we could think of escaping these local minimas with a satisfactory temperature that allows us to escape this because it helps us in the acceptance function. And if we found a perfect configuration, this would allow us potentially to escape all of them and then apply a super selective temperature of 0 that just gets to the local minima, to the global minima. In terms of algorithmic procedures, this implies having a starting configuration, an energy distance function, a number of iterations, a temperature schedule, and a way to sample a kernel, which is the proposal matrix. We just start from this random configuration, and let's do this line by line. R is the random configuration which we start from. For a number of iterations, we sample a candidate which is valid from the proposal matrix. We extract the temperature from the schedule function, evaluate the change in energy. This is just used to sample, to simulate the probability. But if the probability of accepting, oh, this is getting stuck again. If U, which is used to simulate the probability, is less than the minimum of 1 and the change of energy over the temperature, which is the acceptance rule. So if the probability of accepting is, if this number is less than 1, or the change in energy divided by the temperature, the current temperature, we then assign the candidate to R, which is our possibly minimum distance configuration. This choice of the rule resembles the acceptance matrix we saw before, because this is equivalent to accepting with probability equal to the minimum of 1 and the change in energy. If the change in energy is positive, we do not accept, we do not always accept. If the change in energy is negative, we always accept. So otherwise, X remains unchanged, and we go on with the iterations proposing others. This way of scheduling the temperature allows us, as I said before, to explore a space and gradually become more selective as time goes on. But given the assuming that our selectiveness is not enough to get stuck at local minimas, it will allow us to somehow jump out of these non-convexities and get eventually to the global minimum. However, this is not guaranteed, because we cannot really find a temperature schedule which is perfectly used in a single instance of the problem. So we have kind of found a way to solve this issue of traveling salesman problem, and but yet we have to make some observations. First of all, we have made some assumptions along the way that do not make the instance generalizable. TSP is assumed to be symmetric in this case. It could have been asymmetric, making the distances a little more intractable. We could have coded the problem. This is just something I'm I'm like suggesting to you. It's pretty interesting. We have assumed that proposals are symmetric so that they cancel out. So the acceptance rule is slightly easier than what it could have been. We could have proved all the statements. These are in the lecture notes. But basically, we are given a complex problem, which is exploding in combinatorics, and which has a microstate space, which is enormous of all the possible routes, and a macrostate, which is pretty small. It's the number of distances, but yet not explorable, as we need to sample the routes somehow. We cannot like find the distance of the minimum distance route without sampling the routes. We have devised an iterative solution with a meta-heuristic method, which means that it's not an exact solution, and it exploits sampling iteratively, which is kind of satisfactory, because if we use this temperature schedule, gradually decreasing it, we become more and more selective. So we start accepting everything, and in the end, we do not accept anything. This was guaranteed by the detailed balance condition, which is basically, we did not really dive deep into this, but it's what implies all of the properties of the acceptance matrix, of the proposal matrix, and all this. And it's basically the starting point of the assumption of an equilibrium condition, of the fact that the minimum energy configuration is indeed the most probable one, and all of these assumptions. Yet, this proposed solution is not exact, because we need to find, for each case, it's a case-by-case analysis, we need to find somehow optimal temperature schedule, and yet this does not ensure that we found the minimum distance configuration. This is something to keep in mind. So it's a way to find an optimal solution, suboptimal, let's say, solution in an efficient time, but this does not ensure that we will eventually find the global minimum. And so it does not imply that, for example, P is equal to MP and that we have solved the $1 million problem. It needs tuning in a case-by-case analysis, because each instance of the problem is different. So we cannot really find a generalization of this. Yet, it is a clever way to extract from natural phenomena characteristics or methods that can be applied in a statistical manner to sample from a distribution and obtain relevant properties of a process. Also, it is known that a smooth energy function makes simulated annealing redundant. So if we did not have like a highly non-complex problem with a lot of like deep local minimas, simulated annealing is not enough. And it's not like, it's redundant, and it's slower than more straightforward optimization. So I hope this was interesting for you. I am open to questions. I know this is, I kind of think I missed something along the way. So if you have any question and wish to like explore this further, please ask. I'm very open. I know the first time I saw this, I was very like, I did not really get it the first time. It needs some time to understand this thing of the temperature schedule. So thank you for listening to me, and I hope you liked it.
So maybe let's first thank Simone. Yeah, before some questions. Thank you.
Simone, I had a couple of questions.
Yeah, go on.
Ask them. Yeah. So, we are updating the temperature at every iteration. Is that Is that right?
So yeah, keep on asking, please.
So yeah. So first of all, why are we updating it every instant, every iteration? That's my
Okay.
question. I mean, there's got to be a more efficient way, right? I mean,
Okay, so maybe I said this while I was speaking, but if you look at the definition, that's less than or equal. So the proper way is ensuring that the temperature decreases or stays the same at each iteration, so that we are either as selective as before or we become more selective. The idea is this one. So you can think of keeping the distance as equal to infinity for some time, which is basically useless in the end because we are just uniformly exploring. So we are not like getting more selective and we're just accepting everything.
right.
And so the equal to infinity for like some time is useless. So you basically start from some temperature, which is infinity or very big. You gradually decrease, and actually at the end, you keep it at 0 for some time, because when it's 0, it only accepts configurations that decrease the energy. So you kind of make sure that you at least get to near to a local minimum. Because if you keep it at 0, you only accept proposals that decrease the distance, and so you get down and down until you reach like some kind of convergence, some local minima.
Right. Also, how do we choose this Tmax?
How do we, sorry?
How do we choose this value of Tmax for our problem? For
the
solving
Tmax, this
yeah.
one?
Yeah.
Oh,
yeah.
so there's this is what is called a meta heuristic. So it exploits statistical properties, but it is very like dependent on the application. So basically the Tmax depends on the problem you're looking at. The usual approach is having a problem, creating a simulated annealing algorithm, and then trying different configurations until you see that one is somehow satisfactory.
Right. So every problem will have its own Tmax. But for the TSP, what are the factors that go into?
Okay. So think about, so TSP is just a problem definition that requires a number of cities, which can be 5, 100, 10, 2 million, and different distances. So there's not even in this case, there's not a specific rule for a given problem that says find a Tmax, that use this Tmax. You need to like see how difficult is the problem, and so how long you need to create the schedule. If you see the things you have to set are the time and the temperature, and how this temperature decreases. So there's a lot of like things, there's a lot of ways in which you can change this process such that in the end, the final configuration is different. So it's a case by case thing.
Okay.
It's
okay. But offhand, we can't name anything. So we can't name anything that clearly says, okay, Tmax must be within this range for this particular parameters of the problem.
I've never heard of something like this, really. Because think about like 10 cities and 1,000 cities. What's the Tmax? Like generalized to both cases. You just don't know.
Yeah. Right. One final clarification, this is the asymmetric case becomes difficult just because detailed balance is not getting followed there, right?
What, sorry?
The asymmetric TSP
yeah,
towards the end of the slides.
Okay.
That becomes difficult because detailed balance is not followed in the asymmetric process, right? Or am I missing something? Yeah, the other slide.
Okay,
Yeah.
so here we find the iterative solution using the property of detailed balance, which is inflow equal to outflow for each couple of nodes.
Right.
So this is a property of the process. The problem is what the process is applied to. So the detail balance is a property of the transition process. It's not a property of the traveling salesman process. We're just thinking of changing the routes in a way such that there's some equilibrium, but then the TSP instance is just what we apply this framework to. So it's completely independent of it.
Independent. Cool. Thanks.
So I would have one clarification question at least. So if you could pull up the algorithm for the simulated annealing one.
Yeah.
So I just
Okay.
This one. So probably you mentioned it, but what precisely is this K? So there is this K dot.
It's just this is my bad. It's just a notation used in Markov-Chain Monte Carlo processes. It's actually said some slides before, but I kind of skipped it fast forward. K is the kernel, and it's the P matrix. It's the like the oracle from which you sample proposals, valid proposals. It's the P matrix in the split.
Okay.
So K given R is the current route. This samples a candidate, a valid candidate, given the current route. So a route which is not a union of split routes, which is of length n and starts and ends in a city, and is actually the result of a swap of cities given the current route.
Okay, I see. And a second question. So, I mean, I don't know how much this one makes sense, because I can see that there in this simulated annealing, there are a lot of moving parts. But I was just wondering, I mean, like, what are like the instances of, say, traveling salesman problem where this algorithm works well? Or perhaps more interesting, what are the instances where this algorithm doesn't actually work?
Okay, so this is actually a very good question. I have also seen someone asking about the approximation ratio of this algorithm. The truth is that if you think about it, this is not, as you said, there's a lot of dynamics here, which are up to the programmer or the researcher or whatever. So the instances of TSPs in which this works or does not is highly dependent on what a person chooses. There's also a lot of researchers like that are trying to improve this process or like take inspiration from it. So it does not really have a quality of the solution. It's just a proposed framework that helps, conditioned on the fact that it is like well designed in finding a very satisfactory solution in an efficient time. So I don't really know how to answer this question, meaning that there's definitely a lot of TSP instances that can be solved once someone like sets a temperature schedule which is good. And there's a lot of instances of TSP that can never be solved, or a lot of instances of TSP that will be solved if the temperature is set well. So it varies from application to application. It's rather an idea of how to start something, and then everything else is up to the person that uses the framework.
Okay, thanks.
Okay, there's some questions in the chat. So the approximation ratio, Aman, if that's the correct pronunciation, I don't know else. Otherwise, I'm sorry. The approximation ratio for this is not like really possible to find because of this thing of the iterations and the temperature schedule, meaning that it really depends on how well you create on how well you set the parameters. If you think about it, the other two algorithms, especially the greedy one, which eventually finds a solution, which is a local minima, is a procedure that can like just be implemented without parameters to be set. The only parameter to be set is the starting point. So one can think of like just running this and seeing that the solution is on average in a real setting, given a set of TSP instances, log n times theta, big theta log n times the lowest distance configuration. In this case, it really depends on how well you set a lot of things. So I couldn't really find someone that like made a clever study of this, and I don't really think it's doable in the end. Then Kel asks if there's any benefit to decreasing the temperature in a non-linear fashion versus a linear decrease. Yes, I have seen some studies of researchers that, well, usually like the easiest temperature schedule, which is not, if you think about it, and the way I defined it, it doesn't say it's linear at all. It's just a decreasing function. There's some researchers that have stated that in specific cases, still this case-by-case analysis, for example, a logarithmically decreasing temperature is somehow better than other instances of this temperature schedule. Yet this is like really up to the design of the statistician that decides to implement the process. So one can derive specific properties, but I've never seen something like generalizing really well. In terms of programming, you can basically just try a bunch of specifications of this function and see which is the best one. I hope this answers your question, Kel.
Actually, I would now have another question. So you said that in practice, when you're programming this, you guess some bunch of times temperature schedules, and then you try what happens. But I mean, because there are like a lot of options to choose from. Is there like any heuristics that people use, or I mean, how do you actually like in practice use this?
Okay. So there's definitely a set of decreasing temperatures. If you want, I can pull up a list once I find like the golden list of decreasing temperature schedules for simulated annealing. I would say that, so this approach, this algorithmic approach, if you see the metropolis rule up there, up in the slides, it is part of a set of computational statistics methods, which are the Markov chain Monte Carlo processes. This specific field is highly dependent on the statistician that decides what to do and explores possible solutions, possible properties of the sampled distribution, and somehow iteratively adapts the algorithm depending on what he or she or whatever pronoun sees. It's like an empirical approach. It's not there's not a mathematical law. It's rather a method to exploit mathematical laws in an applied setting. So there's not a rule for this. It's really up to the person and up to how experienced the person is at choosing something conditioned on what is seen in the moment from an output. Let's say a very experienced statistician, if it's noticed that there's like some kind of properties of the distribution sample which are not really satisfactory, there will be knowledge about what to do in that specific case, depending on what is happening. For example, whatever serial correlation. This is not related to this problem, but it's an empirical approach. It's not really made of rules. There's guidelines.
Yeah, I mean, I understand that, and I was maybe asking for the guidelines, but I can sort of see now that, yeah, what you need is some statisticians to look at the distribution and maybe make guesses based on that, and that's sort of,
yeah. I can see
sense.
that this is like very far from what you are studying. Like you would expect, like there's a rule for this, and I also don't like this part of statistics, which is just like wander around and find something that works. It's not really like this. If you're experienced, you somehow know what to do. Yet there's a lot of choices. There's like a big deck of cards from which you can choose.
Yeah, thanks.
There's also a message. Do you know of any theoretical results that explore what happens if we take the limit over Tmax? Okay, so still Aman. Okay, if you think about it, this Tmax is just the number of iterations that we do. So if this is highly dependent on the temperature schedule, because in the end, it's not the T of time that influences the decision choice, but it's the temperature that is sampled at that time. So I would argue that we could think of studying what happens if the temperature like decreases somehow in like some way for a lot of iterations. Once it gets to 0, whatever Tmax is after that 0, it doesn't really matter, because after some iterations at 0, it's just going to get to the local minima and never accept anything else. So it's a very interesting question. I don't know of any theoretical results of this, but I don't even see the possibility of applying this, because you can get to very high numbers, but this temperature, once it gets like close to 0, it basically never accepts. So after some point, it's going to become like a greedy algorithm that decreases the distance. But that's a good question. I will give a look and see if I can find something.
Okay, Simone, and thank you for the great presentation. But
actually,
I have to go now.
Just one last question.
Yeah, go on.
Mind.
No, I don't really mind.
Okay. So we keep decreasing the t value at every iteration, right? So my only concern is, what if it keeps decreasing and then it gets stuck at a minima which is just above the global minima? So shouldn't there be a prescription where the t kind of increases also in some places, and then
okay. Yeah, go on, please. Sorry, I was just saying I'm understanding your question.
Yeah, so this method kind of seems to me that it will give you a minima, but it need not be the global minima, because at every subsequent iteration you are constantly decreasing. So your probability of jumping out of a local minima at the next iteration reduces, right?
Yeah.
With every iteration. So how do we avoid that, or how do we is there a way to avoid it?
Okay, so there's a lot of answers to the question. So first of all, the temperature does not, as we said before, necessarily decrease. But yeah, you're right saying that this probability of escaping will get lower or stay the same at each iteration. So you say, okay, we might get stuck in this and never and with a temperature that does not allow us to jump out, because these delta ij is going to make the probability very small. So we just get stuck here. This is right. It's not, probably a thing I did not stress enough is that this is not an exact algorithm. So it can return local minimas, but it has a design such that it's not the first local minima it finds. So upon finding a schedule that can escape these local minimas, it will escape. Some researchers have also studied ways to find, first of all, a thing which I saw, which is very interesting, which is called the kick. So if the exploration gets stuck somewhere, there's like a checking condition. And if it gets stuck, it just jumps out like a frog from somewhere to a completely different place, say here. And maybe here the temperature is enough to just jump and get lower. And if you see this point is lower than the one we were in before. So we improved the solution. Other things that are being studied or were studied, it's actually a very old method around the 80s, are like, if we are not satisfied with the solution and we find that we are kind of getting stuck, let's say here, we just like for some time become less restrictive, and we kind of immediately like increase the temperature and get over this hill. Indeed, what I propose is the starting point of an ensemble of methods that can really change with this temperature schedule. Yes, you're right. A competitive simulated annealing method would have a lot of checks and things that allow escaping local minimas more. But this is a satisfactory solution once one finds the perfect temperature schedule. So it's sufficient. Yet the thing you proposed is one of the things that we're studying, like ways to escape local minimas if one gets stuck. I hope this answers your question.
Yeah. Thanks. It will be, I mean, good if you could share some resources regarding these the other thing that you mentioned, where people
The thing
also
about
increase-
the kick, the thing about the kick. Okay, yeah, sure.
Exactly. So
and I also have lecture notes ready for those that like found it interesting, but maybe did not catch all of it, because I really did not understand a single thing the first time I heard about it in terms of technicalities, because the idea is pretty simple, but the technicalities are not really easy to understand. And I have you covered if you're interested. There's some like easy explanations that translate what is on the internet in a more understandable way. So if you like it, I will share them. I will share them. So
that's great, man. Thanks a lot.
Maybe let's thank Simone again, and then I'll stop recording. Yeah, thank you.